All right, welcome back. This is one of day 18, example one. And in this example, we're being asked to show that the transformation from R2 to R3 given by this transformation of t is x plus y, x, and 2x minus y is a linear transformation. Okay, which means that we need to show that it satisfies the two properties that t, we will say cu is equal to c times t of u. In other words, the transformation of the scalar product with the vector u is the same thing as transforming the vector u and then multiplying it by the scalar. Okay, so that's the first thing that we want to show, and the second thing we want to show is that the sum of two vectors, if it's a linear transformation, is the same thing as the sum of the individual transformations of the two vectors. Okay, so add two vectors together, transform it, is the same thing as taking the transformation of the two vectors and then adding it. So we want to show that both of those properties are true. So for this transformation and these vectors. Okay, so if we plug in, we're going to take C. This is negative 5 times the vector 1, 2. And if we look at this would be negative 5 and negative 10. Okay, so I'm going to kind of treat this like a question mark. This would be negative 5 times the transformation of 1, 2. Okay, so on this side, what we have is the transformation of negative 5, negative 10. Okay, and then on this side, we have negative 5 times the transformation of 1, 2. Okay, all right, so I'm going to go ahead and apply the transformation now to both sides at this point right here. And so on this side, the transformation, so we have negative 5, so this becomes negative 5 plus a negative 10. The second component, the y component, is negative 5, and then the z component is 2 times negative 5 minus a negative 10. Okay, and then on this side, we have negative 5 times. Transformation on this side, following the same transformation properties, is 1 plus 2, 1, and then 2 minus y, which was also 2. Okay, all right, let's go and simplify. We have negative 5 plus negative 10, which is going to give us a negative 15. That's going to stay the same as negative 5. This is negative 10 minus a negative, so positive 10, so it becomes 0. And it's like the same thing as negative 5 times 3, 1, and 0. Well, if I multiply each of these in, this would be negative 15, this would be negative 5, and this would be 0. So it checks off that that is true. All right, let's come over here and see if the transformation of the sum of the matrix of the vectors is this. Let me say that better. Yeah, let's see if the transformation of the sum of the vectors is the same thing as the transformation of the vectors being summed. Okay. All right. So on this side, so I'll have a little bit of a divider there, so you can kind of keep track. So u plus v, what do we have? U plus v, what does that equal to? Component-wise, that's going to give me 0 and 5. We're going to transform the vector 0, 5. So on the side, we're going to have 0, 5. Okay. And then on this side, we're going to have, which will give us, let's go ahead and do that transformation now and compare. So we have, what's that equal? 0 plus 5, 0, and then 2 times 0 is going to be 0 minus 5, so negative 5, which simplifies to 5, 0, and negative 5. Okay. All right, so it's the transformation of u plus v. And then let's look at the transformation of u. Well, transformation of u, we have that right here. That's the transformation of u. This is the transformation of u. We've already done that. So that's going to be 3, 1, and 0. Okay, and the transformation of v, if we can compute that. So we have v was, here it was, so the transformation is going to be negative 1 plus 3. So it's going to be 2. This is going to be -1. And then we have, let's see, -2 minus 3. So -2 minus 3 is going to be -5. All right, and now let's go ahead and if we add these together, uh, adding it together, we have 3 plus 2 is going to give me 5. 1 plus a -1 is 0, and then 0 plus -5 is -5. Okay, comparing the two, they are the same. So that is a linear transformation, just as we expected. All right. All right, let's move on to the second problem in our example here and see what we have there. Okay, so for part B for this example, we were looking at the set of continuous functions. We had the set of continuous functions on the interval from 0 to 1. So that was our transformation was from this interval to the real numbers. And it was defined by t of f was equal to the integral from 0 to 1 of f of x dx. Okay, in other words, a continuous function on the interval from 0 to 1, we integrate it over that value of 0, 1, and that gives us the area of the curve, okay, which is the real number. All right, so let's compute A. And again, we're going to, not A, well, this is the property A, because I shouldn't have called it that. Let's see if the transformation of f plus g is equal to the transformation of f plus the transformation, the transformation of g. All right, let's see if that is in fact the case. And then also, I guess I should have lined it up better. Of CF. Let's see, that's equal to transformation of f. So a lot of this is going to rely on the linearity properties of the integral. So a good hunch is probably this is true just because we know that the integral has these properties. All right, so let's look on this side. So I'm going to start on this side and end up on this side on both of these examples. So um, the transformation of f plus g, what does that equal? It's the integral from 0 to 1 of f plus g dx. Distributing the or breaking up the distributing the dx with breaking up the integrals, we have the integral from 0 to 1 of f dx plus g dx. Okay, and then finally, using the property of integrals, the linearity of the integrals, we have the integral from 0 to 1 of f dx plus the integral from 0 to 1 of g dx, which is, this is the transformation of f plus the transformation of g, which is exactly what we wanted to show. And this, going from here to here, this property is based on the linearity of the integral. Okay. All right, and then over here, similarly, t of cf is equal to the integral from 0 to 1 of c times the integral of f dx. Based on the properties of integrals, I can factor out that constant because it is a constant with respect to the integration. And we are left with c times the transformation of f, which is exactly what I wanted to show. Okay. All right, I hope that was helpful, and I'll see you in the next video.